So in the last lecture we saw about Fourier series, how to represent a periodic signal in terms of the Fourier series. We said that we'll use the eigenfunctions of the LTI system, which are nothing but complex sinusoids or phasors, and we'll use these phases to represent or decompose any given periodic signal in terms of phasors. So this is what we said was Fourier series. In other words, Fourier series of a periodic signal z of t we just decompose the given signal in terms of the phasors, complex phasors, okay. And what are the choice of the phasors? We simply say it's going to be harmonics of a fundamental frequency, and omega here is the fundamental frequency, and we consider all harmonics of it, which is k omega, that is plus or minus 1 omega, plus or minus 2 omega, plus or minus 3 omega, and so on. Okay. And how do we compute these coefficients, the Fourier series coefficients or the coefficients of the phasors? So all we are going to do is just take the inner product and normalize it. So what is the inner product? It is in one period. Okay. So inner product between the signal and the phasor in one period and normalize it with the period. And what is the relationship between the period and the fundamental frequency? It's the fundamental period, which means t is equal to 2 pi. So this is the Fourier series relationship. Why is it called the Fourier series? Because we decompose the given signal as a series, a sum of phases, right? And it was first discovered by Fourier, so we call this as Fourier series. Alright, so we also saw about properties of signals earlier, right? Whenever we studied signals, we said that they can satisfy certain some properties like symmetry and so on. Now, what if the signal that we are considering, z of t, has some properties? How does it reflect on the Fourier coefficients? That's what we'll analyze in this lecture. So what if z of t is even? Then can we comment anything about these coefficients? So knowing these properties will really help and simplify our analysis later. So let's understand how these properties affect the Fourier series coefficient. If z of t is even, then as you can see from this relationship, what does that mean? So if z of t is even, we know that z of t is equal to z of minus t, which means from the Fourier series representation, ak e power jk omega t is equal to ak e power jk omega of minus t, right? This is what it means. So what does this mean? So by looking at the right hand side, you can say that this is in fact nothing but minus jk omega t, or in other words, we can consider that minus sign for the k. So if you compare the coefficients now, so the coefficient of e power j omega t here is a minus 1, whereas the coefficient of e power j omega t here is a1, and the coefficient of e power minus j omega t here is a minus 1, whereas the coefficient here of e power minus j omega t is a1. But the coefficients have to be equal, right? We can directly compare the coefficients on the left and right hand side because we have all the components as such. So comparing coefficients, we can say that a1 has to be equal to a minus, only then we'll have this equality satisfied. Extending this to all other values of k, we have a k is equal to a minus k, which ensures that the sequence that we have here, the sequence of values a minus 1, a plus 1, a2, a minus 2 and so on, this infinite sequence is actually symmetric about 0. So this sequence is symmetric about 0, which means that if you take the negative values of k here, then ak will have the same value as the positive values of k. That's what this statement says. In other words, the sequence that we have generated here, the Fourier series coefficients, form an even sequence. That is, you can change the sign of k and still you will get the same coefficient. In other words, what does it mean? It means that the coefficient of the positive frequency and the coefficient of negative frequency is exactly the same. And this makes more sense. Why does it make more sense? Because if we have the same coefficient for a particular frequency and its negative term, what does it mean? Let's take a particular frequency, some k omega is equal to omega naught. And what we are saying is, for an even signal, this ak is equal to a minus k, which means we will have the component ak e power j omega kt and this component also to be present in the signal, and their coefficients are exactly the same. If the coefficients are exactly the same, then you can say that this is ak of e power j omega kt plus e power minus j omega kt, which put together would actually give you ak cos omega kt, which essentially makes this signal even, because cos is an even signal. So what this tells you is that if a signal z of t is even, then the Fourier series coefficients also form an even sequence. Not only that, by combining these coefficients of the positive frequency and negative frequency, we can in fact rewrite this Fourier series coefficient z of t as completely a decomposition in terms of cos omega t. That is, by combining these ak's for positive and negative, you can rewrite this as k is equal to 1 to infinity ak, so there is 2 times cos omega kt here, 2 cos omega kt. So this is true whenever the signal is even. So this is quite interesting. What it tells us is that if a signal is periodic and it is even, then you can completely decompose that signal in terms of only the cosines, not even a complex exponential, but just the cosines. So if it is an arbitrary signal, then you need the phasors, the complex exponential. But if it is an even signal, then just the cosines are sufficient to decompose that and express completely in terms of only the cosines. Now what happens if it is odd? So let's see what happens if we have an odd signal. So for an odd signal, we have z of t equal to minus z of minus t, once again, which means now we'll compare the coefficients directly on the left hand side and the right hand side. Comparing the coefficients, what do you see? You see that the ak here is in fact equal to minus of a minus k. Why is that? Because the coefficient of e power j k omega t here is ak. And what is the coefficient of e power j k omega t here? The coefficient of e power j k omega t here is, when k is negative, we will get this negative to be cancelled out with the negative of k, which means k has to be negative, which means the coefficient is a minus k and there is a minus sign in front, right? So now we get the relationship that whenever z of t is odd, the Fourier series coefficients form a sequence of odd signal. So the signal that we have here, the Fourier series coefficients, which extend from minus infinity to plus infinity, now form an odd sequence. Okay. Now just like the previous case how we clubbed all the positive frequency and negative frequency together, we can do the same thing here. If we club all the positive frequency and negative frequency together because their coefficients are exactly the same, then what happens? Then we'll have a k to be the common coefficient for e power j omega kt and e power minus j omega kt, and this minus sign that we have here could be brought inside for the negative frequency. Now what is this? This is nothing but a k 2j sin omega t. Now by the same logic that we used earlier, we can now say that whenever a signal is odd, we can now completely decompose that in terms of only sine functions. For even, we can completely decompose that in terms of cosines because cosine is an even signal, and for an odd signal, we can completely decompose that in terms of the sine signals, and we get this representation. This is a simplified Fourier series representation of an odd periodic signal. Okay, and the coefficients now is ak2j, whereas the coefficients here was ak2. So this is true only for an odd periodic signal. So this makes sense because sine is once again an odd signal. So you can express an odd signal only in terms of another odd signal. You can express an even signal only in terms of another even signal. And that's exactly what we are saying here. So there are other interesting properties that we can observe for these Fourier series coefficients. So what if the time domain signal z of t is a conjugate symmetric signal? Okay, that is z of t. When we say time domain, we refer to this representation in time when you plot it as a function of time. Okay, whereas what we have here is we call as Fourier domain or frequency domain representation because we have nothing but the coefficients of each and every frequency component. That is, we have phasors on the right hand side which are different only in their frequency. So the way that we are denoting the different signals on the right hand side is by denoting their different frequencies and the magnitude with which they are added together. So the components on the right hand side denote the magnitude of different frequencies that are present or different phases that are present in the signal that we have. Okay, so what if we have a conjugate symmetric signal z of t in time domain? Well, how does it look like in the frequency domain, or how does it affect the Fourier series coefficients? Let's see that. So what is conjugate symmetry? Z of t is z of minus t star, or in other words, z star of t is equal to z of minus t. So what does this imply? So you take the star here, then that is as good as just flipping the sign here. So if you take the conjugate on this side, so we can bring that inside. If you bring that inside, then you have a k conjugate. Conjugating the phasor is equivalent to just changing its frequency sign, and that's what we get here. Now once again, what we can do is compare the coefficients. So if you compare the coefficients here of e power j k omega t, so what is the coefficient of e power j k omega t here? It's a minus k star. And what is the coefficient of e power j omega t here? It is a minus k. And what is the coefficient of e power minus j k omega t here? It's a k star, and here it is just a k. In other words, this is the relationship that we have for all Fourier series coefficients. So what does this mean? This means that a Fourier series coefficient a k star is equal to its own conjugate. So what does this mean to say that some complex number is equal to its own conjugate? It can happen only when this is real, right? So if we say that a plus jb is equal to a minus jb, then this is true only if b is equal to 0, or in other words, a is a real number. That's exactly what we are saying here. Okay, so we have the coefficients ak to be real. if the time domain signal satisfies conjugate symmetry. So whenever there is a conjugate symmetric periodic signal, then the Fourier series coefficients turn out to be containing only real numbers as their coefficients. This is a very interesting property, and this will help us later in analysis, because whenever we have a conjugate symmetric signal, we know for sure that the Fourier series coefficients have to be real and so on. And if we are going from one side to another, if we are putting together multiple phases and they are all added up with a real coefficient, you know the signal that you will get in the time domain is a conjugate symmetric signal. So this will help us in such analysis. Now what if the signal is conjugate asymmetric in the time domain? In other words, you take the conjugate, you will get minus z of minus t, right? So doing the same thing that we did before, which is nothing but comparing coefficients. What do you get? So this is what we get. So in other words, what are we saying now? The conjugate of a complex number is equal to the negative of that number. That is a plus jb. You take the conjugate, which is equal to a minus jb. We are saying that this is equal to the negative of the original complex number. In other words, we are saying a minus jb is equal to a minus jb. This can happen only when a is 0, or in other words, ak is completely imaginary, is purely imaginary. Okay. So whenever the time domain signal is conjugate asymmetric signal, what we have in the Fourier series coefficient is that it is purely an imaginary signal. The coefficients are purely imaginary. Okay. Or j times are purely imaginary, whereas if it is conjugate symmetric, then it is the purely real signal. Okay. Alright. So in fact, we can see some version of that in these two representation itself. So when something is real and conjugate symmetric, it is basically even, right? So then what you should get is a real and even signal. So combining whatever we saw earlier, we can say that, so if something is a real signal, that is z of t is not only conjugate symmetric but also, let's say, real, then it becomes an even signal. Okay. So then what will happen? Then the AKs will be a real coefficient, and this entire thing could be represented only in terms of cos omega t. So what if something is real and conjugate asymmetric? Then z of t becomes an odd signal. Then the coefficients that we have is purely imaginary. So that's what we are seeing here. It's purely imaginary, and it will be an odd signal because it's only in terms of the signs. So this makes sense, and that's what we are seeing here. Okay. Now what if in the time domain we have a real signal? So we talked about the case where we have a complex signal and we have conjugate symmetry or conjugate asymmetry, and we first talked about even and odd. So even means the signal can be either real or complex, right? Now what if we have a purely real signal? So if we have a purely real signal, what does it mean? So using the same analysis that we had earlier, real simply means that conjugate of the signal is equal to that signal itself. So what does that mean? Then the conjugate of the signal is equal to the signal itself. Once again, compare coefficients. So if you compare coefficients, what do you get? So what is the coefficient of e power j k omega t here? Coefficient of e power j k omega t is ak. So what is the coefficient of e power j k omega t here? So you will get e power j k omega t only when k is negative, which means the coefficient has to be negative, and of course there is a star, which means there is a conjugate. So what do we get? So we get that this is equal to ak. This is the relationship between the Fourier series coefficients when we compare the coefficients on both the left hand side and right hand side and then directly write them down, which in other words means that it is conjugate symmetric. So you take the conjugate, then you get the negative of it, right? That's what we have here. So whenever the time domain signal is real, the Fourier series coefficients start having this conjugate symmetry. This is very useful for us because almost all the signals that we encounter in real life would turn out to be a real signal. And when we want to analyze this signal and you use this Fourier series coefficients, you compute this Fourier series coefficients. From this property, you know that our computation has to be satisfying this conjugate symmetry. So if you're computing this and you're getting something else which is not conjugate symmetry, you know that something is wrong. So you can verify that. And because of this property, in real life, when you want to compute Fourier series coefficients, you don't have to compute the negative values of the frequency. So you don't have to compute the coefficient of the negative values of the frequency, because by this property, it says that there is conjugate symmetry, which means if you compute the coefficients for the positive value of the frequency, you automatically know the coefficients of the negative values of frequency. So by knowing this property, we have reduced our computational burden by half. So this is the usefulness of properties. It helps us in our analysis, it helps us in our design, it helps us reduce the complexity of our systems and analysis. Now we can extend this logic to imaginary signals. So what if our signal is purely imaginary? So when is something purely imaginary? If the conjugate is equal to the negative of the original signal. Okay. So if the conjugate is the negative of the original signal, this is what we have. Once again, comparing coefficients, you just get a negative here, which once again simply means that taking conjugate is not only giving us the negative coefficient, but also is the minus of the negative coefficient. So this simply means that we have conjugate asymmetric signal. So now we can have combinations of these things. So we can have a real signal which is even. Okay. So if a signal is real in time domain, it has to be conjugate symmetric and it also has to be even. Okay. So we can combine these two. So what happens when you combine real and even? So the Fourier series coefficients has to satisfy both these properties. In other words, you can say that ak is equal to a minus k, but a minus k according to this is ak. So when something is real and even, then we have this interesting property where the conjugate is equal to the negative is equal to ak, which means the Fourier series coefficient for real and even is also real and even. So now we are getting interesting properties by combining these two, right? So these two put together tells us that the conjugate is equal to the original signal itself, which implies that the Fourier series coefficient is also real and even. So whenever a signal is real and even, the Fourier series coefficient is also real and even. Now what if the signal is real and odd? So if you have a time domain signal which is real and odd, then we have ak star is equal to a minus k, which is from here we get minus ak, which means the signal is now imaginary, that is the Fourier series coefficients are purely imaginary and odd. Okay. So whenever we have real and odd, the Fourier series coefficients turn out to be purely imaginary and odd. Now consider the case where a time domain signal is purely imaginary and is even. Okay. Combining these two, we get imaginary implies that ak star is equal to minus ak minus k, and evenness implies that a minus k is equal to ak, right. So from this property we see that now we have a completely imaginary coefficient and also it has to be even. So we have imaginary and even coefficients when our time domain signal is imaginary and even. What if time domain signal is imaginary and odd? Then we have ak star is equal to minus ak minus k here from here, which is equal to ak, which tells us that the Fourier series coefficients are completely real and odd. So if you look at this, this is interesting because we had a case where the time domain signal is purely imaginary, but still we could get a purely real Fourier series coefficient whenever the time domain signal was odd. And similarly, we had a case where the time domain signal was purely real, but got a Fourier series coefficient which was purely imaginary whenever the signal turned out to be odd. So all possible combinations exist here, and this is why the analysis of symmetry is very useful, because it tells us exactly when our Fourier series coefficients will have some kind of symmetry, when it will be even, when it will be real, when it will be purely imaginary, and so on. So this analysis is very useful because later when we have real signals and we analyze them in circuits, we need to know what kind of symmetries they will satisfy, because if we know some kind of symmetry exists, our computational complexity first of all comes down, and next we will know for sure that our analysis is right. It simplifies our analysis also. Okay, and if we know for sure that that is going to be containing only real components or only imaginary components, once again our computational complexity comes down, because multiplying two complex number is more complicated than multiplying two real numbers or two imaginary, purely imaginary numbers. So all this analysis helps us in reducing our complexity, computational complexity in our analysis of these signals.